30 miles apart or moving towards each other, each at 15 miles an hour, how long would it take to fly from one end of the bicycle?
No, stop with that, stop. What are you talking about? Stop. So this is number 50 in section 7.2, right? 50. Oh yeah, okay, we talked about this. There's, okay. This guy. Tangent 6x. It's 8x. Yeah.
This is the one
Right? Yeah, this is like a one-step problem. It's a little more you can do with it, but it's not really that interesting. It's trying to point out to you how you can do things to kind of break an integral up and reduce part of it. That's part of what u by parts does. It's why when you have a polynomial piece, you want to let u equal that, because if you do it successively, the polynomial will eventually disappear. Does that make sense?
Yeah.
There's an idea called the annihilator. It's the how many derivatives you'd have to take to kill some given function. So for a polynomial, it's just one more than the degree. Right? Does that make sense? No?
No.
All right, so like x squared. What's the derivative of x squared?
2x.
2x. And what's the derivative of 2x?
1. No, shoot, 2.
What's the derivative of 2?
0.
How many derivatives did it take to kill it?
3.
3 derivatives for squared. So if you have a 7th degree polynomial, how many derivatives will kill it? 8.
Yeah.
That's the separate idea. But it is interesting because it does kind of play into integration by parts. If I have a piece of it that's a polynomial, if only that wasn't there, the rest of it's easy, then you let u equal that piece over and over and over and kill it until you annihilate it. But again, this is not life lessons. This is just math. Don't annihilate the things you don't like in life. Okay? Bad. That's bad. Okay? All right. Coming back to this. We talked about this before, but what would be, I want this to show up. So what should I do here so that kind of shows up?
Break off a factor of 10x.
Yeah, so, all right, so tan x. Yeah, if I break off tan squared x, let's see. Yeah. Then what can you do?
What can you do?
Couldn't you let u equals secant? Because you have it show up in the tan squared x. You can rewrite that as 1 secant minus 1.
Remind you guys. You see tan squared. It's a really simple thing you can do with it.
1 minus secant squared minus 1.
Secant squared minus 1.
That's why I'm saying let u equals secant, because then you have secant show up, so you can just have that secant go over to dx, and then the tan x.
Yeah. So this is just a couple steps away from it. So all I want you to do is to get this, do stuff with it so that it becomes this times something, or plus something, or minus something, or this something minus that, or something, right? They want you to rewrite this integral so that you get that to show back up so you can put it in terms of that interval. There are actually several ways to do that, and this is one kind of direct way, because you can see that would immediately get that to show up, right? There are other ways to do it. Okay, so that problem is not that big of a deal. It's just a little side note that I want to throw at you. Okay, maybe. Okay. Anything else from homework?
Are we doing 7.5 today?
Say again?
Are we doing chapter 7.5 today?
Yes.
Okay.
But I want to start off with, maybe we'll do one more example from 7.4.
Okay.
Does that sound amenable? I'll ask a question for you.
Hey, Mr. Waller, could you do 7.4 problem?
Okay. So what was 7.4 all about?
Fraction decomposition.
Partial fraction decomposition, I love it. All right, PFD. So what this, let's try a problem right out of the homework, let me see. That one looks funky, if only I could read it. Here we go, let's try this one. Well, that might be one you're supposed to do. I don't want to do your homework for you. Sure, we'll do that one.
Spin of the wheel.
0 to 1, x over. Oh, this one's a little evil. Well.
13?
Yeah. That might be a little too evil to start off with, but why is this kind of evil? What do you try to do first with partial fractions?
Complete the square.
Try to factor the bottom, right? The bottom of this one,
No.
factorable. No, not really. In fact, the bottom of this one, does it have real, like, zeros?
No.
No.
How do you know?
Because they're all the same size.
Well, there are things that have all at the same time that have real zeros.
13 prime.
What do you check? B squared minus 4ac, right? Because that's what's in the square root. B squared minus 4ac will be negative, right? So that would have negative, that would have complex zeros.
Oh god.
All right, so let's not start there. Let's not start with that one. We'll build up to that one. That's what you get for just picking. Oh yeah, we'll go with that one. That's the one I was thinking about before. Yeah. All right, this one's nice because it's already factored. Oh, that's right. I want to do synthetic division. Maybe I'll still do that with you. I forgot to bring a handout for synthetic, but I'll show you what synthetic is. What's missing, by the way? I was about to write it. Yes. Okay. This symbol is one symbol. This is one symbol. Yeah, we're missing that. Doesn't make any sense. Okay. All right. So why is this one really, really nice?
Because you just need to factor the top.
Bottom's already factored, right? I don't factor the top.
No?
Well, you can do it. Can you factor the top? When would it be a good idea to factor the top? Why would it be really cool for there to be a 2 right there? Does anybody just realize? If there was a 2 right there,
You can cancel it out.
yeah, it would factor as x equals 1. Sure, these would cancel, that'd be easy as shit, right? So obviously look for that.
I did.
If you can factor the top and something cancels, hell yeah, right? Who was in my class last semester? What do you always do when I give you a function and I want to differentiate it or integrate it? What do you try to do with a function first?
Simplify.
Simplify it. Yeah, right? Okay. So it's already factored for me. Can you guys tell me how this would set up for the partial fraction business?
Is equal to a over x plus 1 plus b over x plus 1
Squared, yes.
plus c over x plus 2.
When does the top have to be linear?
When?
Yep. What is one thing I could do to this that would make the C piece have to be linear?
Make it 0?
X squared. If this was x squared plus 2, that's an irreducible quadratic. It's quadratic, correct? Because it would be squared. It's irreducible because it can't break down. So then this would have had to have been cx plus d over x squared plus 2.
Oh.
So the top always has to be 1 degree less than the bottom. And just remember, this is not really second degree. This is a repeated linear. This is first degree, just repeated. So the top is still a constant. I really want, if you look at that handout I gave you, the top with the BCA stuff, it's always 1 degree less than what the bottom really is. Discounting the repeats. So this is linear. So the top's got to be constant. Okay, maybe. And I really want you guys, yes?
So why do we write x plus 1 and then x plus 1 squared?
Because that's where this would have come from. If that wasn't there, and I had something that looked like that and some other that, why would it end up with an x plus 1 squared on the bottom?
Okay.
Yes. Does that make sense? And you might ask, well then why do you need this? Because I don't know if there was this or not. This plus this would equal something over x plus 1 squared, correct? So I have to account for every possibility. If there wasn't one of these, A will come out to be 0. But if I assume A is 0 and A isn't, you're going to get some weird shit. You're going to get weird shit happen because you didn't give the math everything it needed. So we have to cover our bases. And the math will tell us, oh yeah, you didn't need that. And we didn't know, right? Maybe. So if you don't need this, A is going to be 0. But in general, you need this because it could have been there. Maybe?
I have to watch
Yes?
that.
How is it possible it could be there if A equals anything other than 0?
If A is anything, okay.
Other than 0,
All
wouldn't
right,
there be an
watch
x
this.
plus 1?
Let's say A is 2, yeah? 2
Yeah.
over x plus 1 plus, give me something for this one. Give me a number.
4.
4? Okay. How do you do this?
You multiply that by x plus 1.
Yeah.
This needs an x plus 1, right? So you get 2x plus 2 plus 4, right?
Yeah.
So don't you get something over x plus 1 squared?
Yeah.
Okay.
Right? So this is something over x, this x plus 2 is in the mix, and that's what made a higher power, but still this is stuff over x plus 1 squared, and it could have come from something over x plus 1 and something else over x plus 1 squared.
Why wouldn't you have just another x plus 1 is what I'm wondering.
Oh, because, alright, watch, okay. So stop writing. If I put that, what is a over x plus 1 plus b over x plus 1? Isn't it just a plus b over x plus 1?
Okay.
The only reason there would have been an x plus 1 squared there is if there was definitely an x plus 1 squared to begin with, and there could have been another x plus 1 that would become an x plus 1 squared.
Okay.
We've
snap.
got to cover
We're good.
all of our bases. Because if you're missing something that was there, the math will be freaky as shit. It will come out with answers that don't make sense. Yes?
So if it was the initial thing was x plus 1 cubed, you would have it as x plus
Yes.
1, x plus
1 squared.
x plus 1
Cubed. I love
So you
it.
just go all the way down.
Kick ass. Kick ass. I love it. Because that's the most general place that that kind of thing could have come from. Right? No, you guys really don't like yes?
Sorry to like keep asking questions. So if we do have x plus 1 squared, how do we have x plus 1? Like why would we account for that as well if we're already accounting for the
So
higher
again,
piece?
if I have just something sitting here, what was that? 2x plus 6, right?
Yeah.
Okay. Could this equal a constant over x plus 1 squared? Is that possible?
Yeah.
Look at it.
Yeah.
Could the top be a constant?
Oh, no.
Because it ain't.
Yeah.
That's that simple, right? Could that be a constant? Well, no, because it ain't a constant.
Yeah.
I know my grammar's fantastic. I don't give a shit. My language is bad, but who gives it? All right. Do you guys understand what I'm saying?
Yeah.
Uh-huh.
The only way that it could be like a mixture of stuff up here is if you had this, because then you multiply this by x plus 1, and then you get an x term.
Yeah, because you don't,
Okay.
you don't know what x is, it's not a constant.
I don't know what x is exactly. Okay, maybe.
Okay.
So really, the idea, it's a weird idea. I understand. I think this is like one of the first times you ever do this. But if you go any further in math, you start doing this a lot. We know the form of the answer. It must look like this. And hopefully everybody understands why both of these have to be here. And that definitely has to be there, of course, right? Nobody, thankfully, has a problem with that C piece. It's got to be there because it's there. Okay, I like it. So we know the form of the answer. This feels like cheating in a way, maybe. I don't know. We just wrote that equals that. And I can do that because it has to come from these. Now I can try to figure out what A, B, and C are. So to me, I know, not the most general case, but when I learned this, I was like, shit, yes. I mean, I love the hell out of this thing. It's just so, it really is, the math is not hard. The math is not hard. Even if you don't understand it, we've done some problems, the math is not difficult. But it's just so funky, it was just so new. It was like, okay, this is new, this is awesome. This is not the same old solve for x bullshit. This is, I'm not even solving for, I don't care what x is, right? Okay, after all that crap, what's the next step?
LCD.
Yeah, multiply both sides by this. Let me see you guys are cool with this. What's gonna happen here?
X plus 1.
One of these is gonna die, so the A is gonna pick up the other one of these and this, right? What's gonna happen here?
Pick up the x plus 2.
Yeah, the two of these are gonna die, it's gonna pick up the x plus 2. You guys see? If you don't, it's okay, you can say you don't. And then this guy's gonna pick up the x plus 1 squared. So you could foil, foil, gather all your x squared terms, gather all your x terms, right? So for example, don't I get ax squared? Right? Ax squared? Don't I get cx squared? So what must a plus c be?
2. No?
What's in front of the x squared here? What? Is everybody cool with this? If I were to multiply this out, wouldn't I get ax squared plus stuff? Plus b stuff? Who cares? There's no x squares here, correct? Plus cx squared stuff. Yes? The only x squared terms would be the ax squared and the cx. Are you guys with me?
So a plus c
A
is
plus
1
c
plus 1.
must be what? Must be 1 because that's what's there. That's why we call it equating coefficients. These are the coefficients of x squared, correct? They are. A plus c is the coefficient of x squared. What must it equal? Freaking 1 because that's what's there. Yes? Such a beautiful idea. Meg, you guys are all like, I don't think that word means what you think it
B
means.
also
So
has
what do we
to-
do with that?
B has to equal 1 as well, then, because
Yeah, okay. I don't have to do it this way though, do I? That's the textbook method. What's the better way to do this? What do I have available to me? Are there values of x that would kill parts of this? Yeah, that's the other way to do this. That's the way you definitely want to do this. When can't you do that? If no real value of x kills anything. Then you can't do it that way. Good. We'll see if somebody tries. It was gross. Okay. So what's a good value to pick for x? Say again, -1. Because what's the only piece that would be left alive? And I can solve for b then, right? So if x is -1, what's this? -1, -1, +1.
2.
Wait, I'm sorry. 1, -1, +1, that's better. 1, thank you. Equals. If x is -1, this is dead, yes? This is 0. This is 0. What's this? 1b. Okay, so I know what b is. Isn't that cool? I know what b is. I know what goes here. I know I have one of these.
And then you plug in a -2 to kill the B and A.
Yeah, so if x is -2, see if I can do this right. 4 minus 2 is 2 plus 1 is 3. Is that cool? Then this dies, and this dies.
C equals.
Right. -2 plus 1 is -1 squared is 1 times c is c, so c equals 3. Is that cool? Just plugging stuff in, right? Maybe. And then what do you do to figure out a? Why is a hard? Because -1 and negative, they both kill a, right?
We can just
But
plug
what do
in
I
that.
have right here?
You know what
A plus c equals 1. Remember from the beginning? C is 3, so what's a?
-2.
-2. Okay, so. Now, real quick, we've got those answers, correct? Let me show you the other way to do this. Let me just collect this, and then we'll just verify this the other way. So this would be, A we got to be -2, plus 1. B we got to be 1, and C we got 3. All right, let's verify this doing it the other way, just in case you don't like this one. Or actually, you do have to be able to do the other way sometimes. We might as well see. Okay. So over here, you see if you guys are cool with this. Ax, so it'll be a plus c x squared. Cool. See if we can gather our x terms. I want to do this quickly, and it's just foiling because of shit. X plus 2x is 3x, so I get 3ax plus bx. X squared plus 2x, so it'll be 2c. Is that all right? Did that a little quickly. Hopefully you got that right. You guys see what I'm doing? I'm not wasting time in writing, I'm just collecting. So I got my x squared terms. Everybody cool with that? A x squared. This doesn't give me any x squares. C x squared. Bam. Are you guys okay? Tell me if you're not okay. Tell me right now, because I can see in your faces. Okay, okay, okay. Let's do this the full way. Sorry. All right. A times x squared plus 3x plus 2. Is that cool so far? Right? Bam. Plus bx plus 2b, right? Plus c times x squared plus 2x plus 1. Is that cool? Okay. What are your x squared terms?
A and C.
A plus c x squared. Cool. What are your x terms? 3a plus b plus 2c. And where are your number terms? Constant terms, right? 2a plus 2b. All right. All right. So now comes the equating coefficients. In order for this equation to be true, what must a plus c be? A, oh man. Need one more marker to work. You guys see that? Right? Is everybody cool with that? Why is a plus c gotta be 1? Because it's freaking 1. Yeah, love that. It's gotta be 1 because it's 1. The only way this equation can be true is if a plus c is 1, because that's what's there. So what must 3a plus b plus 2c, that must be 1. And then what must 2a plus 2b plus c, 1. Yeah, all the coefficients here are 1. Now that's not the best thing in the world to see, but
Once you have a linear system of your equations.
now you got a system of equations, right?
Do a matrix.
You can do a matrix if you know how to program in the calculator. Fantastic. I've already got an A and C equation. So if I kill B between these two, I'll have another A and C equation. Correct? But let's just see. What did we get for A and C? We got -2 and 3. It's -2 plus 3, 1. Yes. And you get right? So what I'm saying is, if I multiply this by -2, don't the C's cancel when I add those together? I mean, sorry, the B's. Shaboom. So you get -4a minus 3c equals -1. Am I doing that right? Maybe. No, I looked at the, I looked at the wrong thing, but it's okay. So now I got this equation and this equation. Yes? So I can do -4a. I'm going to leave this as negative throughout because then I just have to multiply this by 3. And then I get -a equals 2, so we're going to a is -2. Is that what we got?
That is the worst. Why would it? Why would
Do you guys
it?
remember doing this?
Yeah.
You remember then you learned matrices, which, no?
What if we never learn matrices?
That's bad, I'm sorry. Then you just do this, what I just did, right? It's fine. All matrices do is it actually makes it into a game, making zeros and ones. Right? It's too bad that students don't do it enough to like it. Students do it enough just to go, well shit, that's new, I don't like that, but
What class were we supposed to learn that in?
176. Pre-calc.
Pre-calc?
Yeah.
Really?
Yes.
Hmm.
Yes.
Or high school.
Yes. And of course, what was happening probably when you took pre-calc?
COVID.
Holy shit. So you might have, in those days, certain
Yeah.
sections were tossed, and that's unfortunately one of the sections that they sort of go, let's just toss this. I'm not going to teach you matrices right now, so I'm sorry. I can bring some.
Do we need
matrices.
them?
Huh?
Do we need them for this course?
No.
Oh, okay, then.
Okay, yeah, then.
Now, looking up here.
Don't care.
I'm done with the partial fraction decomposition, correct? What am I not done with the course?
The integral.
Yeah, now I got to actually integrate. So who knows what the integral of this is?
-2 times natural log of
X plus
X
1.
plus-
Natural log of
Natural
x.
value of X plus 1.
Oh my god. 17.5.
What about this one?
Ooh, it's gonna be X plus 1 to the -1. Over
Negative.
-1 or negative X plus 1.
-1 over x plus 1. Yeah.
Nice.
Oh.
Yeah, because
And then was the last one.
What's the integral of x to -2?
Uh,
Negative x is -1. And why does this work the same way as x? Because that's linear. That's a linear. That slope is 1, so it's going to work exactly as if it was an x there. That's why it's so good to realize when there's a linear function inside is easy. When it's a linear function with slope 1, it's exactly like x. Because the chain rule wouldn't give me shit. It works exactly like x. Maybe? Maybe? Some of you guys are like, I don't know what you mean when you say shit, Jeff.
Yeah.
Sorry. Okay. And then this guy, of course.
3L and X.
L and absolute value.
I'm trying to make a new letter that's L and N together.
Each?
That's just H.
Sort of. Yeah, I guess so. It's already there. Okay. So that's the power of the partial fraction decomposition business. And again, if I had a problem like, where's it go? Was yes. Okay, this one's a little bit. All right, let's do this one real quick because I'm not going to do the whole thing, but I just want to start it off. I think it's a cube. Yes.
7?
Yes.
Okay.
Okay, so can you reduce this? Can you factor the inside of this?
Probably.
No.
Nope.
No.
So it's a repeated irreducible quadratic. So when the inside was linear, we put an A on top, and then we put a B on top of the thing squared, correct? It was repeated. What degree is this repeated piece? It's repeated twice. What
So the
degree is
fourth.
this? No. What's being repeated twice?
Quadratic.
Second degree.
Yeah.
So what's the top have to be?
AX plus B.
Yes, the top has to be first degree with one of them plus,
CX plus D.
yeah, and that equals x cubed minus 3x to the 7 over x squared minus 4x. And what really sucks in this example is there's no good x's that make that die, so you're going to have to do the full equating coefficients thing. You understand? Do you see the difference between, like, I know that this thing, if I just plot this down by itself and said, what degree is this? You would say 4th degree. But how are we looking at it? It is a 2nd degree repeated, right? So it's 2nd degree, one of them, so the top's gotta be linear. This is the 2nd degree that's repeated, top's gotta be linear. 1st degree, the top is always 1 degree below what the bottom is, ignoring the repeats. Maybe? Okay. So again, you would do your multiply by this. This would just die, which is awesome, right? You guys see that? And this would just pick up one of these. So you have to FOIL that bad boy out, collect all your coefficients. Maybe. Oh my God, I love you guys so much. Every time I teach one of these classes, I never want to play poker with any of you. I'm not good. I'll let you know. Yes.
So you end up with an AX cubed. right?
Cool. Yes. So A is 1. Yes. If I read that correctly. Is that an x cubed up top? Yeah, it's number 33, I think, right? You can see that better than me. If that would have been an x squared, does everybody see how? Does anyone see how A is the only x cubed piece? A will end up with the x cubed. It's the only one. Because again, when I multiply by this will cancel. One of these cancels, and it picks up another one of these. Yes? Does everybody understand what I just did?
Yeah.
So multiply by these, this cancels. It cancels here, and one of them cancels, so one of them's still alive, right? AX times x squared is AX cubed. There's no other way to get an x cubed out of all that. So what's A? 1. Okay, we know a letter already. That kicks a lot of ass. And then you keep going, right? So you're sort of hoping that somewhere there's going to be like A plus D is 2, because then you know D is 1, because you already know A is 1. You guys see what I'm saying?
Mm-hmm.
It is very much a puzzle to solve. Don't worry, it's not like you're going to release hell or something. Hell works. Yes?
So the x squared minus 4x plus 6 squared under the cx plus d, that cancels out because
So I'm multiplying both sides by this, right?
Okay, yeah.
So I write blah, blah, blah squared, so dies, dies. Blah, blah, blah squared, so dies, dies. And then one of them cancels with this.
Okay.
So that's the list. So then when you do ax times x squared, that's ax cubed. Nothing else you do is going to make a cube. That's why a had to be 1, because it's the only coefficient of x cubed. Now obviously there's more stuff to do. Yes?
Since there is no x squared, does that mean whatever?
What do you mean? There's a bunch
no
of
x squared in the original.
Oh, I see.
So
Whatever
the
those
coefficient is
coefficients
0.
are, it was the 0. If it's one coefficient, if it's a combination of things, they have to add to be 0. Yes?
And then as you get these, like the A's and the B's, you can just start plugging them in and
Yes,
narrowing things
totally.
down. Okay.
Okay, so let me take one more step, because you guys are all looking at me like crazy. So ax cubed, yes? Let me see if you guys are cool with this. Let's do this the smart way. Ax cubed. Minus 4ax squared plus bx squared. I mean, let's just collect things in order, yes? Minus 4ax squared plus bx squared. So I get plus negative 4a plus b x squared. Yes, yes? Minus 4ax squared plus bx squared. Plus 6ax minus 4bx. Yes? Yes, yes, yes.
Mm-hmm.
And then I get 6b. And then I get my cx plus d. Okay, so now, for example, I know a is 1. I know 6b plus d is 7. Yes? Okay, right? Yes, yes?
How is 6b plus d 7?
Where are my where are my constant terms?
Oh, okay. It's just 6b and then d.
So those are the constant terms on that side, so when you combine them, it must be 7 if this equation is true.
For the 6a minus 4b x, shouldn't you have the c in there as well, since the c?
Yeah, of course. I mean, that was just getting this.
Oh, okay.
And now you can put the cx with this guy in. So now, for example, so there's your ax cubed. This one I'm going to have to fold in the, any more x squares? No. So this is good. B minus 4ax squared. And then this one, I've got a cx, so I can do the 6a minus 4b plus cx. Gather all your stuff. All your like terms, right? That's all this is. We don't like terms. So what must b minus 4a be?
B minus 4A.
No, 0. There's no x squares here, right?
So B equals 4.
And a was 1.
Yeah.
So b is 4. Hey, we got 2 letters already.
Okay, I am doing this right.
Okay, and then here you know a and b, and you know that 6a minus 4b plus c must be negative 3, and you already know what a and b are. So this one's a relatively nice one, to be honest, yes?
How do you know what B is already?
Okay, a is 1, is that cool?
Yeah.
Okay, b minus 4a must be 0, and we know a is 1. We already knew a is 1, correct?
Oh, okay.
As you learn what the letters are, you can plug those values in. They're not unknowns anymore. Yep. No, you don't have to love it as much as me. You don't have to love it at all. You just have to be able to do it.
If it makes you feel any better, I love this more than anything else we've learned so far.
Okay. Sure. Is that good? It doesn't tell me
Not saying much.
what degree it is. You're like, there's no love, and this is where I am. Right there. Yes.
So the last one is ax, still ax cubed, or is that?
This guy?
Yeah.
Yeah, it's an ax cubed from the beginning, and a must be 1 then? Okay. Okay, okay. So it really is just a puzzle, which some people love, some people hate, I understand. I personally love it, it's a little
See,
puzzle.
this is nice because
Yeah.
you're just basically doing algebra and then you're integrating them
Okay.
polynomials, so it's like not, you're not doing any
Now,
kind of fancy trick.
Very
integration.
often, once you do partial fraction, you'll end up with a bunch of natural log stuff,
Yeah.
Mm-hmm.
but not always, right? Sometimes you have to do U
Space
subs, sometimes you have to do trig subs, I mean, whatever has to happen after you get it broken up. They're like a new problem now, you have to treat one thing at a time. Yes.
So I know this is mostly just algebra, but are we also gonna be using like trig with this?
Like I just said, once you get these broken up, right?
Yeah.
And you figure out A, B, C, and D are, you'll have to look at each of these integrals and try to figure out what process will work.
But like sine, cosine, tangent.
Could be.
Okay.
It could totally be a trig sub. It could be a U sub. Yes. I mean, it could be whatever the hell it has. So the first step is you're actually creating what the problem is. You're given this problem, and you're breaking it up into two more manageable problems, but you still have to figure out what the hell those problems are. You still have to figure out what process to use. This was nice because it was natural logs and linear -2. That's nice to integrate. This probably won't be as nice because they're going to have this thing on the bottom.
Yeah.
Yeah.
I was just about to ask.
But the constant piece over this will be easy, relatively. Well, we'll see. We'll see what you guys can do.
Because you have to combine the two expressions, right? Like after you find out.
No,
like,
after you
A-
break them up, you want to put them back together? No.
Ooh, good point.
Yeah. Okay.
Yeah.
All right. So you just have to get in there and try some of these out, and bring questions. Staring at me doing some of them will not show you how to do them. Got to try them out.
So once we have. Oh, at that point it's just like U sub and stuff like that,
Could
right?
be, yeah, it could
Okay,
be
okay.
U sub, it could be whatever.
I got it.
Then you have to evaluate what you're left with.
And
Yeah.
I mean, yeah.
I see.
So you could basically be going straight up, straight down.
Could be. Yeah. Okay. Maybe. So that's going to happen always. You've already seen this happen. You're in Calc 2. You've seen this kind of thing happen where you do one step in the new chapter and then suddenly it's some idea from an earlier chapter, maybe even the class before that. Right? So that's a little daunting because anything you've ever learned can suddenly show up. Yay, that sounds good.
I don't remember.
What do? You just calm down. You try to take it what it is, and you get some help if you need it. And as you do more of these, you'll start to realize things to look for. Okay, I'll stop. Okay.
I'll start chapter 5.
Section 7.5 is absolutely nothing new. 7.5. Remember when I was talking to people earlier before class kind of started. Remember when you learned factoring, and there was that section that was just basically all the forms of factoring?
Mm-hmm.
Just mixed up? Okay, that's what 7.5 is. It's all the forms of integration just mixed up. They do give you, if you read the section, they give you a shitload of help. So, does anyone remember what I keep saying? If I give you an integral, what do you check for first?
Simplification.
Say again?
Simplification.
Good. Can you simplify what you were given? Right? So, for example, if I gave you this, does anyone feel good about that problem?
What do you mean by
Should.
what do you mean by
Because what can you do first? Pull the 3 down. It's a log, right? So I can just pull the 3 down.
Oh.
I can make that into better. That's what I'm talking about, right?
Yeah.
And of course, last semester I gave something like this. I don't know, blah, 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 blah. Let me see, blah, 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 blah. There. Holy shit! Oh man, is that U sub? Do I have to complete the square? Oh shit! Do I have to use partial fractions? How do you factor this?
X minus 1, X minus
X minus 1, X minus 7, X minus 1 cancels, and then it's just a natural log. Damn! Alright, so when I give you, now I'm not saying it's always going to simplify. No, shit, no. But if it does simplify, hell yeah, you want to see it. So, very first thing you do, does what I'm given simplify? Right? Definitely look out for this. Now, what's the difference between this one I had up here a second ago and this one? Are those the same?
Oh.
Hell no. What's being cubed here? X. What's being cubed here? Easy? Not easy. Quick? Not quick. Right. Even this is not really quick because you still have to integrate natural log, but we've done that before. That's your most basic, that's the first thing you do almost always when you learn by parts. Is the integral in natural log. Okay, maybe? Okay, so very first thing, can you simplify what you've been given, right? What's the next thing after that?
Right.
And actually, there's one thing before that, is just a straight up integral. Right? Because I'll do stuff like, what's the integral of secant squared x minus sine x? And I'll have people multiplying by the conjugate or doing some kind of weird trig sub. Why is that not hard? It's just freaking straight integration, right?
Yeah.
What's the integral of secant squared?
Tan x.
Oh, shit. What's the integral of sine?
Cosine.
Negative cosine, so it'll be plus cosine, right? Plus c.
Oh, I thought we were counting them.
Is that all right? You guys
Yeah.
with me? And basically, they have these steps on page 504. Simplify if possible. Look for, now, part 2 for them is look for an obvious substitution. I would say part 2 is look for the obvious, just straight integral, right? If it says integral secant squared, don't do any trig shit. It's tangent. Yay! And then worry about the rest of it, right? Yes, am I with me? And I still get people that sometimes, what if it was this? What if it was this? By the way, this is a dot on the I, not a -2.
Mm-hmm.
Well,
A little hump.
secant squared x is still
Yeah, you
10x.
can, so for some reason people forget that you can break an integral up. That's easy. For some reason I still get people that are like, they think they're supposed to take care of both of these at the same time. Supposed to get a u sub that works for both. No, break that integral up. That's easy. And then you can just worry, and now this is easy too, right? This was on some of y'all's quiz.
Yeah.
Okay. But still, it's not direct. It still requires a little bit of work. It's not that bad. That's all right. You guys get what I'm saying here. So this section is kick-ass. I would highly recommend, if you've never done this before, read this section. Read the book. Try it, right?
What is the page?
Do that. Oh, page 504. And page 503, now depending on which version of the book, I think the numbering gets a little weird if you have a different version of the book. But it's section 7.5. First page has a giant table of integration formulas. That's not giant, this is about half page. And then the next page has a step-by-step. Here's the things you try, kind of like a recipe of attempts. Let me attempt this. If that doesn't work, this is the next thing I think, right? Don't try to memorize this. Try to see why it makes sense that these are the things you do. Why is u sub thing, looking for u sub, why is that one of the first things we try? Because it's relatively easy, of course, right? So of course I'm going to look to see if u sub works. I'm not going to look for integration by parts first, because that is more difficult, period. U sub is easier.
How do you even identify integration by parts?
Okay, so,
Like if nothing else, you're just like,
You just try
let's
it.
try that.
let me see. Yeah, okay. Alright, this is not the best example, but one was a little too in your face, obvious, hopefully. Is this a by parts?
No.
Why not?
You can use sub it.
There's a function in there whose derivative is also in there. It's free to move,
Yeah.
right? Now watch this, watch this. Oh, by the way, what's this?
By parts.
Because this is one of the most obvious by parts, and by parts are not always this obvious. But I put something that I could do, and then I threw a freaking polynomial on it. Damn it! You checker! So then you can do a by parts, like u equal this, so it will die, right? And this is integrable, which is a hard word to say. Integrable. Makes you sound like you're drunk. Okay. And I'm not drunk, I don't think. Okay. What if it was this instead? So this is easy, this is u sub. Kabam. Why can't you use u sub on this the way it's written?
Because the derivative's in the bottom.
Yes. If you say, now again, I get some people that still, if u is tangent and du is secant squared, I do not see this. That is not in there. That is not in there. I see 1 over secant squared dx. I can't construct by du. Yes?
I have a question. What if you added a third power of secant to the top and bottom, and then you did u equals secant x?
Now you're talking. Now you're talking. But my point is, you can't do anything the way it is.
Mm-hmm.
So what you just suggested is really cool. Because you would want u to be secant in this case, correct?
Mhm.
Because it's the part that's stuck. And like you just realized, what's the derivative of secant?
Secant x tan x.
So if only you had a secant x tangent x up here, well, you can just multiply top and bottom by secant. Right?
Damn.
That's beautiful.
That is really cool.
So at least you can identify that this is not U sub, and it's not by parts yet. You don't want to make it by parts yet, but it is something you have to do some trig identities, or you do something like multiply top bottom by secant.
And now it is U sub.
Because if you let U equal secant, du will be secant tangent. So that's du, and this is U cubed. Right? And then it's easy. 11. Yes?
So, for a lot of problems, could you make them into methods that you feel more comfortable with if you know how to get them there?
Of course.
Or, like,
If you know how to get them there.
Right.
That's the key, right?
but will it be impossible to get some problems to?
There are some integrals that are impossible to do. I don't think I assigned any that are impossible to do, I'm pretty sure.
Okay.
But there definitely are a lot of integrals that are impossible to do by hand. And then you have a class called numerical methods, which involves a bunch of ways to integrate things. Anyway, we won't go.
Okay.
That's where you start bringing computer programming in. It's a really cool one called the Monte Carlo method. So if you want to write that down, you can look up Monte Carlo integration method. It's one of the coolest methods. Sorry. Yes.
Oh, I was gonna say, can't you do like tangent of x times 1 over secant, which is 1 over cosine, and then just be like tangent of x times cosine squared of x?
Sure. So this will become, if you bring this up, it'll be tangent x cosine squared x. Sure, right? But how does that help you? That is true. That's true. But how to, and there's nothing wrong with writing that, just looking at it and going, that did nothing for me, right? Now you could make this,
Yeah, sine over cosine.
okay, good. Yeah, so then you can keep going. So that would be, all right, let's see. Now I'm really curious. So we can make that sine over cosine, so one of the cosines cancel, isn't that cool?
So it's just
Does
sine.
anyone see what to do here?
You said.
U sub, sure. And somehow that's gonna come out with the same answer as doing it this way. These are the same problems, right? Yes, these are the same problems. These will come out to the same answer. They won't necessarily come out to look the same, but they will be the same answer, just maybe separated by some identities. Does that make sense? So sometimes if you pick a different way than the book thought of, and you go to check your answer, you could have gotten the right answer. It's just in a different format. Maybe.
Can you also multiply the integral by 2 over 2 and then make it sine 2x? Do the integral.
Oh, sure, yeah, that's what I was thinking, like this 1/2 sine 2x. Right? Does everybody see that? What's sine 2x?
2 sine x.
2 sine cosine, right? 2 sine x cosine x. So if you put a 1/2 out front, you can put a 2 inside, and that's just sine 2x, and that means beautiful. Look at that. There's 3 freaking ways to do this one integral, and they're all relatively equal easiness or hardness. Okay, maybe. Now, some of you guys hear that and freak out because you're like, just give me one way. Just tell me exactly what to do. And that's too bad. That ship has sailed. We're getting closer to real life. We're not in real life yet. Even at Calc 2, you're not fully to real life yet, but we're getting really close. And what does that mean? Multiple ways to do shit, because that's freaking real life.
Is Calc 3 real life?
Calc 3 is some real shit.
Okay.
Calc 3 is awesome. Anyway, it's been a while. I want to teach, maybe I'll teach Calc 3 next year, but I want to teach Calc. It's been a while for me. I love Calc 3.
What is Calc 3?
Multivariable
Plus
integration.
Calc 3, real quick. Let me teach you Calc 3 real quick.
Z.
Don't you normally have an input of x, and you get a function, yes?
Yeah.
Ooh. Now, can you imagine the xy plane, and you have a function of x and y, and the output is z?
I don't like this.
So for every point in the xy plane, you have a different output up here. So then you get this, you can get this like sheet, right? So for every point, you get a different output. You with me a little bit?
Yeah.
And then you can ask, what is the volume
Oh god.
under that sheet?
So what is
That
that?
sounds a lot like what's the area under this curve. Doesn't that sound the same?
So what do you use to calculate the volume?
Like what would that
Double
integral look
integrals.
like?
Triple
Double
integrals,
integral.
Yeah.
Okay.
Is that related to like washer method and stuff?
No, it's not directly. I see what you're trying to do. The washer stuff is really for like a repeated shape, because when you rotate, you get all these circles, and that's why you can do this process. But there's every shape in the world, like a cross section of a circle? No. So that's why Calc 3 comes in and says you can have some freaky looking shit and still develop the volume, which is a lot like, okay, that's enough. Sorry. It's enough Calc 3, maybe. But I mean, this is cool. I want you to be psyched about this. If you're going to take Calc 3, I do want you to be a little excited. You are going to go into the third dimension finally. We're still in 2 dimensions here. That's kind of pathetic. Well, that sounds terrible, but you know what I mean? You're like in Calculus 2, we're still haven't gotten out of the plane of the board yet, right? Calc 3, you finally come out of the plane of the board. And some of you guys are like, that's fine with me, just keep it in the board. Yes?
How do you even draw a Calc 3 model if you're doing it on a whiteboard?
Oh, it's not easy.
No.
Oh, when I took Calc 3, like 3.7 million years ago, my teacher had to draw for us everything. There was no computer program that would really do it well. So he's drawing everything, and he drew it about as well as I do. So you're all like, what is that?
Can we just skip
Off
7?
the top of it.
Not right now. I'm sorry, not right now. I did too much.
We're about to skip 7.5 altogether.
Skip the whole textbook.
I appreciate that question, Manny. I'm sorry. I gotta get back. I really want to, but I can't.
Can we do it after class?
After class, I can do.
Okay.
We gotta get through what we have to do in Calc 2.
We have 20 minutes to do it.
Yeah. Unless you want Calc 3 on your test. I'll keep talking about it if you want it. Okay, so they have a decent number of examples to go through that kind of talk about the reasoning as to what they do. So the big thing for you guys is, let me see if you guys understand this. Some of you guys have heard me say this. Any individual problem you're working on doesn't mean shit. Each individual problem you do doesn't mean anything. What's important is what tells you what to do next. What's the motivation? What has the problem got in it that tells you what to do next? If you can't get a certain problem, there could be some certain thing you're not seeing for that problem. But what's important is, do you know what to try to do? Right? You guys follow with me? Okay. And I didn't just say the homework doesn't work. That's not what I said. Hopefully you understand what I'm saying. Okay. So 7.5, like I said, it's a lot like when you learn grouping in one section, and then in another section you learn trinomials, and in another section you learn how to factor squares and cubes. And then you have a section that says everything. That's 7.5. So there's nothing new in 7.5. Nothing. It's just more true to what the test is going to look like. Test is going to be a mash of integrals. You just have to figure out what method to use. Okay. So 7.5 is awesome practice. It's also going to possibly be very frustrating. Just, right? Just honest. So if the problem is really giving you all the trouble, pass it by. Come back to it. Okay. Even better, come in and get help. Now, I used to do 7.6. I think the department decided to make it optional a while back. 7.6 is kind of neat because it does reference the table of integrals in the back. I think I will do some of that kind of thing later, but just to show you how to use some of these. If you ever looked at the table of integrals in the back, in the reference section, you should just take a look at it, see what the hell's going on. But what we're going to do tonight, let me see if you guys, let's see, last time we got not much. Do you guys remember, let me just draw a couple of pictures, see if you guys remember what this is about.
What chapter is this from?
Huh?
What chapter? 7.
7.7.
Riemann sum? So Riemann's.
M-ram?
Anybody?
R-ram.
Riemann, you're doing.
Riemann is Rams. Riemann sums?
Yeah.
Riemann, yeah. You guys remember Riemann sums?
Yeah.
You should probably remember it a little fondly because it was just areas of rectangles. That's all it was, right?
It was pretty nice, actually.
So, how wide are the rectangles? You guys remember the symbol?
N?
Delta X.
Delta x. N was the number of rectangles, correct?
Yeah.
And let's say this is A, this is B. What was delta x equal to? And N is the number of rectangles.
B minus B over S.
Yeah, B minus A, how long I gotta go, divided by how many rectangles are gonna fit in there, will tell me how wide each rectangle has to be. So this is relatively straightforward. So of course now we're gonna take that and make it more interesting. You guys remember how, depending on how ugly the function was, if you didn't use enough rectangles, your estimation was pretty far off, right? In fact, here you can see it's under here and over there a bit, so maybe that'll kind of, and the function's sort of up and down a bit, so it kind of averages out. So whatever this function is, if I did Riemann sums with this many rectangles, it would probably come out pretty close. Are you guys seeing that? It's under here, right? Under, over here, under, over. So it's probably gonna come out kind of close, maybe a little over. You guys see that? Is that cool? Okay, just so you remember, rectangles are not the best shape to try to fit a curve, right? Okay. In fact, what method is this? There's two kind of methods.
Right endpoint.
This, yes.
Yeah, so this one's a right endpoint, because the height is determined by the right end of the rectangle. Then you have left endpoint. What it kind of makes both of those better?
Midpoint.
Midpoint, right? So we already know this. We already know left endpoint, right endpoint, midpoint. The midpoint would just say you establish these and then you figure out what's in the middle. Of course, it's amazing. That's why we call it midpoint. Wow, Jeff. Okay. So, some of the cooler methods to use. One is called the trapezoidal method. It's just fun to say that. It's sort of like freakazoid. Trapezoidal method. And the other one's a little less interesting, but we named it after the dude doing props, Simpson's method. To me, Simpson's method is much more interesting. Okay, you guys semi with me? So the ones we know so far, left endpoint, right endpoint, midpoint, which one does the best at approximation? Midpoint. Because it kind of factors in an averaging of it, right? You guys with me? No? Yes? So, let's talk about trapezoidal. Let's see if I can do this. I'm going to try to recreate the same picture. Let's see if I can do this. Okay. So the trapezoidal method, just focus on one of these. Yeah, let's focus on this one. So I still have delta x, still is the same thing. However many trapezoids you want to use, right? Still the same thing for delta x. N is the number of trapezoids. What's the trapezoid look like? There's a few different answers you can give me. What just happened? Somebody just drew a line. Okay.
It's like a triangle and a square.
Two triangles.
So here's a standard trapezoid here,
Well,
right?
it depends.
parallel
Yeah.
lines.
Right?
Two triangles.
All that needs is two lines to be parallel and the other two lines aren't.
Yeah.
Because otherwise you'd be parallel at everywhere. Is this a trapezoid?
Yes.
Yes, totally, cool. So watch this. What if I connect these like this?
Oh. I
Right.
like this.
Big brain.
I make a trapezoid. And then I can do the same thing for over here. So these are, this is basically that, just whoop. Right? So that is a trapezoid. What is the area of a trapezoid? Let's identify a few things. This is the height, correct?
Mhm.
This is kind of like on its base, but this is the height. This is base 1, this is base 2. Does anyone remember the area formula for a trapezoid?
B2 minus B1 divided
No.
by.
Like B
Thanks for
times,
playing.
isn't it like base times height times
The average
1/2?
of the two bases times the height?
That's
Well,
what-
yeah, okay.
That's what I was.
I like, I'm
that's-
sorry. I didn't said minus. Didn't you?
Yeah. Oh,
Well,
did I?
okay.
Sorry. B2 plus.
So there's your B1 plus B2 over 2 is the average of the two bases times the height. That's a good way to remember. I always remember, what's the area of a triangle?
1/2 base times height.
Half height base, half height base. Okay, sorry. Wait a long time ago, I was trying to make a stupid song. Half height base, but there's two bases, so you just put both of them here, right? So trapezoid is basically a triangle, it's got two bases, same thing. So it's like a decapitated triangle. Poor little guy. So, what is this? So the height, the base 1, base 2. So this is like the height, correct? It's just been, but what is it on my picture here? What's this? Delta x, I got you. Delta x. Then you have, so 1/2 the height times the sum of the bases. What's this base?
1, 1.
Okay, I like it. Be more, there we go. What's this? F of A, I like it. Yeah. Let's see, f of x no, right? Plus f of x1, yes? Yeah. Alright. So everybody with that, that's the first trapezoid, correct? Okay, I need some more room here. I'm gonna erase this guy up here. It's a very Christmassy thing going on. Oh shit, well it's alright. We all know what the area form is. So what I have so far, the area of trapezoid 1 is 1/2 delta x times f of x0 plus f of x1. What's the area of trapezoid 2 gonna be?
F of x, same thing but with f of x1 and
1/2 delta x times
F
f of x1
and f of x2.
plus f of x2, right? And that's gonna keep going until you get to area trapezoid n. So be f of x n minus 1 plus f of x n. There it is. You did it. So everybody sort of, so again, just like we did the rectangles, now of course what's missing to kind of get what I actually want? I want the area under the curve, from there I want this area. So what do I do with all the trapezoids? Add them all up. So look what happens. I'm gonna take this picture away now, I think we got it. Thank you. Take somebody's belly and shoot, all right? Yeah. It's a perfect job. It's been cut in half, all right. Look what happens if I add all these up. So the area of the trapezoids, trapezoidal approximation for the area will be 1/2 delta x. I can factor that out of everybody. F of xo, 0, plus I'm gonna get 2 of these, 2 of everybody, correct? 2 f of x1 plus 2 f of x2, all the way up to f of xn. And you, is that right? Now what's a little bit funny here is the trapezoidal method comes out a little worse than the midpoint method.
Oh.
Yeah, normally, most of the time. So yay, we learned a new thing that's worse than something we already knew. Yay, Jeff, go team. But let me see if I can lay some groundwork for the next thing. And we'll probably call it a night. By the way, real quick, Monday, yeah, Wednesday I'll have the practice test. And next Monday, wait, am I thinking correctly?
Yeah.
This Wednesday is the 14th, correct?
Yeah.
Okay. So next Wednesday is your test. So this Wednesday I'll have the practice test. Next Monday I'll have an answer key. It'll be a review day. And then we'll have the test. What else is happening next on this Wednesday?
Sign.
Yes, another quiz. Yes.
Is 7/7 gonna be on the test?
I don't know. We'll find.
Okay.
Oh, yeah. Well, this is 7. Yeah, this is 7/7. This is totally gonna be on the test.
So we're gonna have to do all the adding part on the test?
I
This is
really
just a
want you to understand.
Prereq.
If you don't have, guys, if you don't have shortcuts to doing this, I will show you. There's shortcuts on the graphing calculator, right?
Okay.
So,
I think I found them.
Yeah.
But
so this is just like Riemann sums used to be. The funny thing is, it just has these extra doubling things.
Mm-hmm. Okay.
But if I just showed you this formula, you'd say, where did the 2 come from? And now you totally see where the 2 came from, right? Because each trapezoid shares one side with the next trapezoid, right? Except for the beginning and the end. So of course it makes sense there's 2's in there. Now, that's the trapezoidal method. And I've got a handout, don't freak out, so something kind of nice to reference. Let's talk about Simpson's method a little bit, and then we'll head out of here. Simpson's method Simpsons did it. Simpsons method is the best. And if you want to approximate something that's curvy, wouldn't it make sense to use something that's curvy to approximate it? I like it. So if I want to approximate this, when I use a parabola, doesn't it look parabolic? Is it parabolic?
Probably.
Nope. I'll tell you for certain it ain't, because it's part of a cube, right? But it looks pretty close to parabola. Right? So the trapezoidal method, the rectangular method, they use straight lines at the top, right? So that will always be worse than if I used a curve. Does it make any sense? No? All right, so let me see. Let me try to draw the same picture again. What was it? Was it basically that? I can't remember. So this is A, this is B. I still have my delta x. A is also known as x0. Is that cool? All the same kind of stuff goes into it. But now, let me ask you this. If I want to use a parabola, how many points do I need to find the equation of a parabola? How many points do I need to find the equation of a line?
2.
2. So if you give me any 2 points, that defines a line. You give me any 2 points, how many parabolas go through those 2 points? Infinite number. Just like you give me 1 point, how many lines go through that 1 point? Infinite number. So if a line needs 2 points, a parabola needs 3. Holy shit. And why does it make sense? Because what's the equation of a line? Mx plus b. There's 2 parameters I need to know, so I need 2 pieces of information. What's the general formula for a quadratic, for a parabola?
X squared.
Ax squared?
Plus bx plus
3 unknowns, I need 3 pieces of information. Is that cool? Okay, so that means I'm actually going to use 3 of these points to construct a parabola that goes through them, right? So, let's see, so I got this point, and roughly this point, right? So this will be f of xo, f of x1, and f of x2. Funkydelic. So just to kind of make, I don't know, make this, I don't know, that's probably not right. Try to, this is almost parabolic you've just done, Jeff. Good job, buddy. I'm trying to make it different. Let's say it's like that. That's horrible. If you look at the computer-generated images in the book, if you want something nice, right?
Cute.
Huh?
I like it. It's cute.
Oh.
It has
Little
heart.
guy. He's cute. He's had a rough life.
Underdog.
So we have this, right? We have this. How do I, okay. I want to find the area under this thing, correct? Help me out here. If I shifted that whole picture over, would it change the area there? If I just picked this whole thing up, this included, and just moved it over, would it change the area? Of course not. If you have a triangle sitting there, and you move it over there, it doesn't sound like double in area. That'd be neat. We need more triangle. There we go. No, unfortunately, the perspective doesn't happen like that, correct? So, to make this easier to think about, this might be where I have to stop, just for myself too. I'm going to move it so that I'm going, in fact, let's do 2 things. Let's call delta x h just for a moment. Let's call it h. This feels a little bit like limit as h goes to 0 stuff, but don't freak out. Just to make this easier. So do you see how this would be, if I move this over so that x1 is right here, right? What would this be?
0.
This will be negative h. Is that, x1 is 0, correct? This will be h back. How far apart are these? H, delta x1, I'm calling it h. So if I move this until x1 is 0, this becomes negative h. It's h back. So of course, what's this one? H. That's going to simplify our work a lot, and the reason it's legal is because, of course, it's going to be the same area if I move it over. So why not move it until it's got nicer shit to look at? Yes, maybe. Okay. me see. Oh, Jeff, you left us a lot to do in the minutes. All right. So, do you see how I want to integrate? Now, what would the area be here?
The integral of the
Integral is
parabola
from
from negative h to
negative h to h. This is not hard, correct?
Yeah.
I didn't tell you A, B, C, who cares? It's freaking quadratic. Easy shit, yes? So what do you get?
Ax cubed over 3
Yeah, 1/3 ax cubed.
plus bx squared over 2
Good. 1/2 bx squared.
plus cx.
Cx evaluated from negative h to h, correct? Okay. And then you throw some h's in there. So I'll tell you this. I don't want to try to, if I try to keep going, it's too long. We got a little bit of a ways to finish this up. So what we're gonna do is we know this is what we want to get. And then I've got to relate it to stuff that we already know. So the next thing we're gonna do is do that. We're gonna make that connection. And we're gonna end up with something that looks a lot like left endpoint, right endpoint, midpoints, trapezoidal rule. It's gonna have the same look. It's just gonna have different coefficients. And here, let me give you this. Sorry. So I kind of, spoiler alert, you'll see on this one what it's gonna be. But you don't know why it's gonna be that yet. And then we still have to talk about the error. Don't worry about the error yet.
So we're skipping 7-6, yeah. I mean,
Yes,
yeah.
7-6 is not in our curriculum.
Okay.
So what's the point of trapezoidal if it's not as effective as midpoint?
Because there are situations where it is better and it's easier to program, or the function you know it's just going to fit better with it. There are situations where it's better.
Useful in Calc 3?
Not really.
Can you show us a Calc 3 function now?
Okay, so if you're interested,
Class is over, you can leave.
Calc 3.
I kind of want to see it too.
I got
I'm
curiosity.
not even
man.
gonna take it. I'm interested.
I have to take it. I just looked and I'm like, I have to take it for transfer. I'm like, damn.
Anybody who has a moment, I'm going to show you something really kick-ass. You don't have to stay if you don't want to. If you want to stay and see some Calc 3,
I gotta see Calc 3. I said, no, we're gonna see Calc 3.
so the outputs are now Z. So do you see how my inputs have to be a full point?
Yeah.
So for example, if I input the origin, what do I get?
0.
That's a me. If I input 1, 0, what do I get?
1.
0, 1.
1.
1, 1.
2.
Crazy shit, right? But here's the trick. The XY plane is now like our x-axis used to be. Over every point in the x-axis, I could have an output for a function, correct?
Mm-hmm.
So I put the x value in, and I would get a y value out. Now I'm putting an entire point in, and I'm getting something, and normally how we try to represent 3 dimensions is like that.
No.
It's not very good. And then there's actually, it's called orthogonal paper? I think it's orthogonal graphing paper. Isometric, maybe. Isometric graphing paper, where they got the little cubes, and you can actually make it really 3D.
Yeah.
This is attempting to be, right? This is our best attempt by him. So for 0, 0, it's 0, right? So this is the x, y, z. So my xy plane is here, yes? Here's my xy plane, yes? And my z is like that. So like if I took it and rotated it and put it like that, this would be coming out, so I just turn it like that. So it's all in 1 dimension, but it's 3 dimension. All right, so see how difficult it is to graph this? By
Yeah.
It's like impossible. So watch this. This kicks so much ass. Even if you don't know how to do any of this stuff. All right, there we go. One of the coolest things, and I did not help this student do this, but one of my students in Calc 3 a few years ago created this program because he was also a computer, it's called Plot. He's not a computer, he was a computer software major, so Plot Ninja. Hopefully it's still up. It's been a while since I looked for it. Yes. So watch this. So right now it's this. Look.
What the
Well,
hell?
let's do x squared plus y squared just to do something a little more straightforward.
Okay.
So that kind of is like what you expect, right? Now listen, I really want this to make sense. So this is Z, correct? If I make Z 0, that's 0, 0. That's the bottom of the cone, right? And I'm looking straight at it right now. You guys somebody with me? If I make Z 9, can anyone tell me anything about Z equals 9? What's the equation? It's a circle. Every cross section at different values of Z is a circle. And what's happening as I let Z be bigger and bigger, my circle is getting wider, and that's why the cone grows as you go up. Yes? Maybe?
Okay.
So Calc 3 is number 1, understanding how this stuff works. And see how I was trying to show you the cross sections? It's kind of cool.
Oh.
I mean, he did an awesome job with this. It's
yeah, this is
insane.
really nice.
Just imagine teachers trying to draw this shit. So as you move up, look at the Z getting bigger and bigger. Of course the circle gets bigger because Z is basically the radius. It's the square root of the radius. Yeah, so I mean, if you just want to play with this website, the original thing they had up here, what was the original thing they had up here?
Sine and cos.
Yeah, this is kind of cool. This looks like an egg carton kind of thing.
Because they're waves.
Yeah. But now it's cosine and sine wave going forever in both directions. Yes.
So in Calc 2, do we like revolve figures at all?
I mean, part of the problems could have been solids of revolution, right? Those are kind of boring, to be honest. I mean, you have to learn them to get the idea
Because
that
I did those a lot in high school. I didn't know if they were
1D integrals, and not to say that they have no purpose. It's fascinating to see a 1D integral representing a two-dimensional object.
They didn't feel purposeful.
Oh, well, sorry. So there's plenty of objects that are created that have rotational symmetry. And so those lead to volume formulas for those objects. If I know the function defining the edges of it, correct? Then I can do that kind of thing. That does happen. It is not
So that's not this.
contrived. This is not something that has rotation to it. Has that been rotated? No. It exists on its own. It's not a 2D thing that I turn. That was Calc 1. Calc 3 is truly three-dimensional shit. It's not built on 2D shit that's been turned. This is just a three-dimensional thing, right? Do any of you guys, egg card. You guys, egg card? But this is like it forever extends in both directions. It's the infinite egg card. Maybe? No? Okay. That's enough. I don't have any more. Okay. Yes. Let me show the people at home. There you go, Plot Ninja.